Hello students, let us start our new session of chapter 13, Kinetic Theory. Now let us understand the example 13.1. The density of water is 1000 kg per meter cube. The density of water vapor at 100 degrees Celsius and 1 atmospheric pressure is 0.6 kg per meter cube. The volume of a molecule multiplied by the total number gives what is called molecular volume. Estimate the ratio or fraction of the molecular volume to the total volume occupied by the water vapor under the above conditions of temperature and pressure. So here the mass of molecules are given and the density is less as its volume gets increases. So here volume of a vapor is available 1000 kg per meter cube for the water, and for the vapor that volume is available 0.6 kg per meter cube. By taking its ratio, we can define that volume of the vapor is 1000 divided by 0.6, that would be equal to 1 divided by 6 into 10 raised to minus 4. So by this amount, the volume of water is larger. Now if the density of this water, bulk water and water molecules, if we are considering same, then the fraction of molecular volume to the total volume of liquid becomes 1. And volume in vapor gets increases, so the fractional volume is less by that amount, 6 into 10 raised to minus 4. Let us understand another example. Estimate the volume of a water molecule using the data which is available in first example. So here now we need to estimate the volume of water molecules. So in the liquid, the molecules of water are bounded with the higher atomic forces. So the density of water molecules, which is available 1000 kg per meter cube, that is equal to the density of bulk water. Now the volume of water molecules, for that we need to know the mass of single water molecule. So for that 1 mole of water, that would be equal to 2 plus 16 gram, that is 18 gram converted into the kilogram, so that is 0.018 kilogram. So 1 mole contains 6 into 10 raised to 23 molecules, so 0.018 kilogram contains how many molecules? So let us divide by the molecules of 1 mole and we will get 3 into 10 raised to minus 26 kilogram of mass. So this is what the mass of a single molecule of the water we are having. So here volume of water molecules, that can be defined as a mass per volume of water, that is volume of one molecule, mass of one molecule 3 into 10 raised to minus 26 kilogram divided by volume of water 1000 kg per meter cube. So this is how we are getting 3 into 10 raised to minus 23 meter cube. And we know that volume that of these water molecule, which is a spherical surface having the equation 4 pi 3 pi r cube, make the subject of formula r and be able to get its radius, that is 2 angstrom. Next, what is the average distance between atoms in water? So here the mass of water in a vapor condition is available as a 1.67 into 10 raised to 3, which is that amount of times greater than the volume of the same mass of water. So here if we increase the volume in which the number of molecules of the water is also gets increases. So here volume is increased by 10 raised to 3 times then the radius is increased by 1 by 3 times. Then volume raised to 1 by 3. So here the radius, in earlier example it is available 2 angstrom. So volume is increased by the multiply of 2, that is a 20 angstrom. So the average distance is available between atoms, that is twice of 20 angstrom, that is 40 angstrom. Now, a vessel contains 2 non-reactive gases, neon and oxygen. The ratio of their partial pressures is 3:2. Estimate the ratio of number of molecules and mass density of neon and oxygen in vessel. Here, partial pressure of gas in a mixture is the pressure that would have for same volume and temperature which is occupied in vessel. So the total pressure of a mixture of non-reactive gases, that is a sum of partial pressures due to the Dalton's law that we have derived. So here, volume and temperature we are keeping constant for these 2 gases, and pressure variation is available. So ideal gas equation, we can write down that PV mu RT, which is what the ideal gas equation, in which P1 into V equal to mu 1 RT, and for another gas P2V equal to mu 2 RT. Now take the ratio of both the equations. So we are having P1 by P2, that would be equal to mu 1 by mu 2. So here we are having that pressure ratio is available in example, that is 3:2. So if P1 by P2 is 3:2, so mu 1 by mu 2 is also available as 3:2. And we know mu is equal to N1 by Na and mu 2 equal to N2 by Na. So here, this N1 and N2, which are the number of molecules available in gas 1 and 2, and Na is the Avogadro number. So by taking those ratio of mu 1 and mu 2, we are getting the ratio N1 by N2, that is again equal to 3/2. And in terms of mass, we are having that value mu 1, that would be equal to m1, small m1 by capital M1, and mu 2 equal to small m2 by capital M2, where small m will define the mass of gas 1 and 2, and capital M defines the molecular mass. So here, if we are taking its density of the gases, so that mass density rho 1 and rho 2, that will give you mass per volume m1 by V divided by m2 by V. So we are getting the ratio m1 by m2, that would be equal to mu 1 by mu 2 into m1 into capital M1 by capital M2. By substituting the ratio mu 1 by mu 2, that is a 3/2, and molecular mass of the gases are given. By substituting those values, we are having the density ratio 0.947. Now let us understand kinetic theory of an ideal gas. Here, as we know, the interaction of molecules in a gas is negligible. So, based on the Newton's first law, it can be identified that molecules are moving freely with the constant velocity in straight direction. Now, due to, as we have defined the atomic hypothesis, in which while molecules are far apart at some distance, then they are having attraction force. Due to that, they are coming close to each other, and as they are coming close to each other, so their intermolecular force is dominated, which is increases, and their velocity gets changed. And as they are coming together, collision takes place. So after this collision, molecules are changing its velocity in terms of change in the speed and change in the direction. These collisions we consider as an elastic collision. Now let us understand the pressure effect. Okay, so here these molecules of the gases are available in a random motion. So they are colliding with each other. towards the wall. So all these collisions between molecules are available between molecules and walls, which consider as elastic. So total kinetic energy is conserved, and based on that, momentum is also gets conserved. Now based on that, let us understand how the pressure will work onto this ideal gas. Here, as you can see in the diagram, we are taking a closed container in shape of cube. Now we are taking at a time only one molecule, and we are defining its velocity. This cube is placed and identified with the 3-dimension x, y and z. Now we are assuming that this molecule is moving towards the x direction by keeping y and z direction parallel to it. So here, this molecule, in which its velocity initially available vx, vy and vz. Now while it is moving with the parallel to y and z axis, then velocity component of y and z remains constant and velocity component of x gets changed. So this molecule is moving by the x direction, and that is colliding onto the wall, which is elastic collision. And after colliding onto the wall, this molecule rebounds back and in the opposite direction. By changing its direction, its velocity gets changed and becomes negative. So after collision, the velocity of molecule is available as minus Vx, Vy and Vz. Here, as velocity gets changed, momentum variation also takes place. Linear momentum equation, we know P equals to m into V. So let us consider change in momentum, that is a P2 minus P1. P2, that is m into V. M, mass of molecule. V, let us consider in x direction variation, that is minus Vx. And P1, that is mvx. So minus mvx minus mvx will give you twice mvx. So here, final momentum after collision, we are having minus mvx. So momentum collision while imparting onto the wall, that would be available twice mvx, as the conservation of momentum takes place and momentum remains constant before collision and after collision in a reverse direction. Now, calculate the force onto the wall. For that, we know force equal to momentum per time, and time interval, let us take delta t. Here the velocity we are focusing onto the x direction. So the distance covered by the molecule from the wall, that is velocity equal to distance per time. So distance equal to velocity into time, that is Vx into delta t. So here, whatever the number of molecules are present within the volume of A into D, volume means L cross L cross L. L cross L will give you the area, and that L remaining we consider as a distance covered, Vx into delta t. So volume we supposed to define as A into Vx into delta t. So all the molecules within this volume can hit the wall in that delta t time duration. Now half of these molecules are moving towards the wall and half of the molecules are moving in other direction. This is what we are assuming. So for that, let us understand how many number of molecules are present within this volume. So here, number of molecules are present which consider as A Vx delta t volume into n, that is the number of molecules. Now from that, half of it, that is 1/2 A Vx delta t into n, which are hitting onto the wall, and remaining molecules are moving in other direction. So how many total momentum are carried out by this number of molecules? So here Total number of molecules, total momentum can be defined as Q equal to momentum due to single molecule into total number of molecules. So we have determined the momentum due to single molecule, that is twice mvx, and we have also determined the number of molecules present which are hitting towards wall. So that is 1/2 NaVx delta T. By multiplying this, we are able to get total momentum of the molecules which are transferred towards the wall. Now, let me know force is what? Force onto the wall, that will give you the momentum per time. And pressure, that we are having force divided by area. So pressure equal to momentum divided by area into time. Right, momentum we are having Q divided by area into delta T. So let us substitute the equation of total momentum Q from the 13.10 equation, and we will get pressure equal to m n Vx square. Here we are assuming that all molecules are moving with the same velocity. So total pressure we are having n m Vx square. Here we are taking the average velocity of that Vx square. Here we are taking gas is isotropic. So no preferred direction of the velocity is identified in the molecules, and we are taking, it's a symmetric structure. Vx square equal to Vy square equal to Vz square. So that would be the average velocity, that would be equal to 1/3 of Vx square plus Vy square plus Vz square. That would be equal to 1/3 of V square. So total pressure can be defined as 1/3 Nm V square. Now by the whole process and the derivation, 2 points that we can summarize. First, we have derived that pressure equation for the container of cube. Now, if we are taking any vessel having a arbitrary shape, so for that we need to choose some smaller area. We need to carry out these whole steps, and we need to determine its area and delta. While we are determining these particular steps, we can determine the total pressure by integrating all that individual pressure amount in small area. By getting that equation, we can define that area and delta T will not reflected into the final result, same as for single molecule in cube shape. So here, in equilibrium state, pressure is the one portion of the gas that will be remain same everywhere of remaining portions also. Second summary can define that we have ignored over here collision. So here, whatever the number of molecules are there which are moving towards the wall and hitting onto the wall in delta T time duration, that we have determined 1/2 of NaVx delta T. And these collisions are random in gas, but these collisions are not that much frequent, and the time required to collide between them, which is also very much less. So this collision we can neglect, and above process we can consider as it is. Clear? Here we are going to end this session. Hope you understood. Thank you.